I am Sabbir Molla, and I will be presenting the paper named Mitigating Object Hallucinations in Large Vision Language Models Through Visual Contrastive Decoding. And this paper was published last year in CVPR, and it already has 151 citations. With me in my team, I also have Inad Al-Quraishi, Anaf Munir, Qingyang Liu, and Shouraf Agarwal. This is how we're going to present today. First of all, we'll quickly discuss what is object hallucination. Then we'll move on to what are the primary causes of object hallucination. We'll quickly move on to the proposed method, which is visual contrastive decoding, or also known as VCD, and then an improvement upon it with adaptive plausibility constraints. Later on, my teammate will explain the experimental setup and results, ablation studies with discussions, and also limitations and conclusion. So before going to object hallucination, let's quickly look at hallucination in general in large language models. This has been an active topic ever since the advent of these large language models. And this is the phenomenon where large language models can generate text that sounds plausible, that are very much human-like, like natural language, but can be factually incorrect. So, for example, if you ask a model who was the first person to walk on the moon, the model might respond, it's Charles Lindbergh. But we know that that's factually incorrect because the first person to walk on the moon was actually Neil Armstrong. So we say that the model has hallucinated here. This translates to large visual language models where, given a prompt with an image, the model might simply describe it. The description might include objects that are actually not present in the image. So, for example, given this peculiar image, and if we ask the model to describe it, the model can start pretty well. It can say the image features painting of a brown dog, etc., etc. But then we see that the model starts mentioning dining table, fork, table, etc., which simply does not exist in the image. So in this scenario, we say that the model has hallucinated these objects. So why does it even matter to discuss about this topic? Well, the authors say that it's important because hallucination can mislead decision making because these large visual language models are being used in lots of domains that can include healthcare, autonomous driving, and robotics. So just think about the panic that a model in a healthcare can cause when it misdiagnoses a tumor. Or think about a car or a self-driving car that suddenly stops because it has hallucinated a stop sign. Or maybe think about a robot in a warehouse that is trying to put some materials in a shelf that is not empty. So that can cause some hazardous accident. There are some existing solutions that try to address these issues. And these solutions can fall under the post hoc category, which means that they use some different models to kind of correct the output of the first model. And there are other category of solutions that say that maybe we can annotate some new data sets that does not have this kind of hallucination problems and train the model using some tricky technique or some technique like reinforcement learning. However, as I said, both of these approaches rely on external tools and rely on training, which increases cost, and maybe that's not expected. So before moving on to the proposed method on how to address this issue, let's quickly go through what are the primary causes for object hallucination. And these causes are statistical bias, language priors, and visual distortion. Let's go through them one by one. Statistical bias. You see, most large visual language models are first pre-trained on some data sets like maybe COCO, and these data sets have certain classes that appear much more frequently than other objects. And also these data sets suffer from frequently co-occurring objects where certain classes tend to appear more frequently together, but in contrast to other objects that do not appear together. For example, if we see this distribution of the classes of Coco, we see that certain classes like person, car, dining table appear in a lot of images, whereas certain classes appear in only a few hundreds of images. So any model trained on this dataset will simply be prone to hallucinate on these frequently appearing objects. And about frequently co-occurring objects, we can look at this image, which is an image of a dining table, but we can almost always expect that dining table co-occurs frequently with classes like person, cup, bottle, chair, etc. And this statistical bias, we can observe it by doing some analysis on models like MiniGPT-4, Lava, Multimodal GPT, MPlug-OWL, and we see that these models tend to hallucinate more on classes like person, dining table, and chair. And if you recall, these are the same classes that appears the most in datasets like Coco. And then we can also see an example of hallucination of co-occurring objects, where if you provide these models enough images with dining table, they tend to hallucinate more on classes like person, chair, cup, and that is because these objects usually co-occur the most with dining table. So language priors is also another reason for object hallucination. And this occurs because these visual language models rely excessively on the language patterns. This may be because these models have been pre-trained on large natural language datasets that have imbalances or bias in themselves. And also, common phrases might dominate the output, where in a visual language model, we don't want that because we want the output to be consistent with the image. If you look at this image, if we provide the image to a model might say, this is the image of a woman's portrait, but her eyes and eyebrows are replaced by eyes and eyebrows. That makes no semantical meaning, but it seems to be correct, but we know that it makes no sense. Then visual distortion is another reason for object hallucination, and visual uncertainty or distortion, in fact, can increase the both statistical bias or language prior, which leads to an increase in object hallucination. And this can be validated by incrementally adding noise and gradually seeing the large visual language models' performance getting degraded. So this is an analysis from the paper which show that as we add more noise to the images, so we increase in the number of steps of noise, the accuracy or F1 score both gets lower and lower. So the more noisy the images are, the more the models start to hallucinate. So for a quick summary, we have three factors: language priors, statistical bias, and visual uncertainty. And all these factors create hallucination, which we aim to mitigate via the proposed method. And the proposed method is called visual contrastive decoding, also known as VCD. The way VCD works is, first we take the image and get the logits. Then we create a distorted version of the image, and we get also the distorted logits. And finally, we subtract the distorted logits from the original logits. And we'll go through the equation later, but the way VCD works is simply we subtract these two logits. Now, if we see VCD in action, if we have an original image and the same image but distorted, we can pass them to the same model. If we don't do anything or don't do VCD, the regular decoding, as you recall from an earlier slide, gives us some nonsensical answer. But if we apply VCD, we can see that the result is way better, because it says painting of a dog wearing a headband and dress. In contrast to the regular decoding, we can say that this is far better. Now, let's try to create an intuition for VCD. If we have an image of a black banana, it is expected that we want the logits for black and dark to be high enough. However, since the model knows that a banana should be yellow or green, we see some high value in the yellow and green logits. But since we have already seen that visual distortion increases in the object hallucination, so this distorted image of the banana will get even higher logit in yellow and green. And if we keep adding noise, we see that more noise we add, the more the logits for black keeps decreasing, whereas the logits for green and yellow keeps increasing. So our aim is finally to remove these logits from our initial original logits. If we try to understand it mathematically, this is the equation for VCD, where we have as input our textual prompt. V is our original image, V prime is the distorted image, and we want to get the distribution for the next token. And on the right-hand side of this equation, we have the logits for actual image with V, and the logits for the distorted image with V prime, and we simply get the subtraction. Alpha here is just a hyperparameter that regularizes how much we want to remove from the actual image. And the reason why we have 1 plus alpha here is so that no matter whatever value we choose for alpha, the left-hand side of these two terms, so this left term will always be greater. And with softmax, we make sure that these logits will eventually become a distribution for the next token. As a recap for what alpha is doing here, the best way to understand this is if we put alpha as 0, this disables our contrastive decoding, and this left term 1 plus alpha will become simply 1, so that means we have back our regular decoding for any large visual language model. More on the values for alpha will be discussed later. So what are the pros of this VCD? It penalizes hallucination, so it decreases hallucination, and it makes sure that the outputs are closer or more consistent with the input image. It also offers, it basically offers a training-free method that avoids any extra cost because we don't have any external data set or any external model. It lowers the over-reliance from language priors. Hence, it maintains minimum computational overhead. Now, VCD has some challenges which the authors propose to solve or address by using adaptive plausibility constraints. So let's go through the challenges first. So VCD penalizes entire model's output based on the distorted images result. So you have some good logits from the original image, and you are changing all the values from it from a distorted image, and obviously that can cause some issues. And this indiscriminate penalization might sometimes lower the performance. And another reason for this is because the assumption was that the distorted visual input increases object hallucination. But maybe that's not always the case. And for those scenarios, VCD will lower the performance. So we can summarize by saying that VCD can introduce improbable tokens that should not appear, so it can just increase hallucination. Let's quickly look at an example of when that can happen. Imagine we have this good image of a car, and the model is very confident that this is a car, so it assigns a 0.70 value. But it is also starts to hallucinate a little bit on the cat. Then we put a distorted image of the car, and this time the model is not hallucinating as much. It is still very confident that this is a car, maybe a 0.60. So if we apply VCD here, you see what happens. 0.7 minus 0.6 is 0.1. Similarly, 0.2 minus 0.1 for cat, we have 0.1. So after VCD, this is making that car and cat will have the same logit. So when we sample from this distribution, we are basically increasing our hallucination because our original model images output was actually better than VCD. So to solve this issue, we use adaptive plausibility constraint. And the idea is that we first create a set of tokens where the original image's output was very confident. And this is the equation for that. So V hat is the set, and we consider for all tokens in the vocabulary. We want the token's probability to be higher than a certain threshold. And beta is a hyperparameter that just regularizes the maximum logit that we got. And all the probabilities of tokens that are not in the set are simply set to 0. So we say that the VCD probability will be 0 if the token's output was not confident enough in the original input's output. Hence, this technique ensures that VCD does not introduce any new improbable token. The final formula by combining VCD with adaptive plausibility constraint looks like this, where we basically want to sample the next token Y from a distribution where we basically take the logits of the actual image and subtract the logits of the V prime, that is distorted image, and we make sure that any token that is not confident enough in this part is set to 0 by subjecting that YT belongs to that set. And now my teammate will move on and start describing the experimental setup and results.
Oh, okay. Now let's move on to experimental setup and results. For the dataset, we have POPE, MME, Lava Bench. For matrices, we have accuracy, precision, recall, F1 score for POPE, accuracy and accuracy plus in MME's official framework, and GPT-4V based accuracy and detailedness on Lava Bench. So what is basically POPE? POPE is a benchmark that evaluates if the model is hallucinating or not. So the idea here is to basically ask yes-no questions based on the responses of the LVLM. It will decide whether the object is hallucinating or not. So here there is an image given with like a bunch of fruits and there is knife on the table, and we ask the model, is there a bottle in the image? And the model replies, yes, there is a bottle in this image. So here this is an example of random setting where we ask the model if the bottle is present or not. Clearly there is no bottle present in here, but it says yes, which is a proof that the model is hallucinating. Then there are, broadly speaking, there are three settings, random, popular, and adversarial. So in popular setting, the idea is to ask such kind of objects which are popularly known to be present with those objects. So here we have fruits, and it is very common for images to be having knives in it. So again, we ask, is there a knife in this image? And the model responds with yes, there is a knife in this image. Similarly, we ask about the pear, and it replies with a yes. Looking at the POPE results, we see that VCD outperforms baseline in random, popular, and adversarial settings. As you can see here in the results table, there is an increase of about 6 points in the F1 score. Moving on to MME. What is MME? MME is basically another benchmark which is used just for, not only for existence, but it also checks for the counting attributes and more on the qualitative side of the image. So previously in POPE, we were just checking if the thing is present or not in the image for hallucination, but here we go a little bit more into depth to check whether it is telling us the number of count or the color exactly. So for example, here we ask if there is an elephant present in the image. It says no. Again, it is hallucinating. Let's look at the example of the color. Is there a red coat in the image? As you can see, there is a red coat, but it says, it replies with a yes. We ask if it is yellow, and it says no. So we can, in this case, check that the model is not hallucinating. Looking at the MME results, VCD outperforms regular decoding. As you can see, there is a significant jump in the score from 565 to 604, and there are also strong color gains. Lava Bench. Here is another benchmark used for the evaluation. In this case, Lava Bench is basically a set of 24 images and 60 questions. So here the idea is to ask open-ended questions rather than asking yes-no questions, which we were doing previously. So the idea is to map how good the model is able to do the cognitive task. So we can ask things like caption the given image, and it's able to caption something, and basically the model will check whether the caption is aligning with the image that is given at hand. And that's how you can check for hallucination. Looking at the results, we can see that there are significant improvements across LAVA 1.5, Instruct Blip, and GraalVL. Looking at the overall results, we see that VCD consistently improves across a POP, MME, and LAVA bench. There are no trade-offs, meaning that it's able to benefit the model in all the cases. It's not like we are trying to implement VCD and the model is becoming extremely conservative and is not able to deliver as much. That's not the case. Model agnostic, that means it's able to work on a different variety of models and is just not limited to a single model or two. And it's stable, and it's able to work well across different hyperparameters and decoding strategies. And the main advantage here is it's training free. So it can be used in real life situations. Moving on to ablation studies and discussions. Noise steps. Noise is basically, we are trying to introduce noise in the image, and the goal is here to make the model focus on the visual and should not shift focus on the language priors or other biases that the model has. So we see that if we increase the value of T too much, that is, the distortion is too much and it's not able to identify the image clearly, the performance is not good. If the distortion is too less, that is not good enough to force the model to rely on the visual cues. So it turns out that a moderate amount of noise is the best. And here are the results. With the moderate amount of image, the hallucination is best mitigated. Effects of alpha. Here is a quick recap of the formula that we talked about. And once again, moderate alpha gives the best trade-off between correctness and cohesion. Effects of beta. Again, we see that the moderate value gives us the best result. And beta basically filters out the low confidence tokens. And we are here trying to protect the valid tokens from over-penalization so that the model's integrity is intact. Here are some of the results. Sampling strategies. VCD maintains and boosts performance under diverse sampling strategies, meaning that it's not just able to perform on some of the sampling strategies, it's able to do best on top P, top K, greedy, etc. And it's able to show consistent gains across different temperatures and hyperparameters. Talking about model scale, even the large model scale suffer from hallucination. And for example, LAVA 1.513b, they do have more hyperparameters. That's why there is even more risk of hallucination. And we see that VCD is able to perform good for these large models as well. Here you can see for random LAVA 1.513b, there is an increase of approximately 5-6 F1 score, and similarly for others. Looking at the future directions, advanced distortion techniques could be looked into. Right now, what we are doing is just using the basic Gaussian blur, which basically creates noise for the whole image rather than just dealing with the particular object level or region-wise permutations. And now that the VCD only works for image, meaning that it is only working on a single image frame, but in the future we could also take it one step further and put it in video and multimedia expansions to improve on the temporal domains. Hybrid approaches. So right now we just are using VCD. However, if we do want to improve it further, we can enforce it with reinforcement learning with human feedback to improve on factual grounding. And finally, cross-modality and cross-lingual. As for most of the things which are predominantly focused on English language, we can think about expanding it to other languages. Limitations. Let's talk about limitations. Although it is training free and everything, but still there are some limitations which we have to look into, and there is a lot of scope of improvement. So currently it relies on Gaussian noise, as we discussed before, for distortion, leaving room for other advanced techniques. It's primarily tested on a single image task, and extending it to video and other modalities is still unexplored. It requires a strong visual encoding, and performance may vary. Let's say if there is a model which is not as strong when it comes to the visual encoding, then it's not able to perform that much. And further analysis is needed to refine adaptive constraints to handle subtle cues. So right now, it may struggle when it comes to the finer details of the image. So to conclude, VCD yields an approximately 7.4 increase in F1 score when it comes to POP and 18% on MME, which shows a robust performance. Once again, VCD is training free and lightweight, which eliminates the need for additional dataset or models. VCD generalizes well across LAVA 1.5 in strict blip and QuenVL, which highlights its widespread applicability. VCD also simultaneously improves general perception. So we are not only mitigating hallucination, but we also are improving the cognitive ability of the model. All right, thank you.